Okay. So this is problem 71 from chapter 26. Here we have a Wheatstone bridge. So there's some complicated circuit, it's quite busy. So we have 4 resistors here. One of them is a variable resistance. These are labeled R1, R2, and R3. R3 is variable. And there's this Rx, which we are required to find. We have these vertices labeled A, B, and C, and D, and 2 currents, I1 passing through this way and I2 this way. And there's an ampere meter here and a switch that's currently open over there. So a Wheatstone bridge, I've drawn here a simpler version, just with a resistor instead of an ammeter, is a typical irreducible circuit. So there are no parallel or it's the simplest irreducible circuit. There are no parallel or in series resistors, so you can't use this by using the rules for parallel and series resistors, right? You need to apply Kirchhoff's loop rule and junction rule and so on and so forth. So this is an example for solving that exercise. But it is a practical use. It is a use for determining the resistance of a given resistor. So here we are trying to adjust this R3 in such a way that when the switch is closed, this ammeter is going to read no current. And when that condition is satisfied, then this unknown resistance can be given in terms of these other 3 resistances. And the question is asking, what will be that expression? What will be the expression that gives that unknown resistance, the 4th resistor in the circuit, in terms of the other 3 resistors in the circuit? Now, when we close this, if no current is passing from B to D, then it means that B and D are at the same potential, right? So if B and D are at the same potential, whereas C is at a higher potential than B and D, then any charges arriving over here is not going to move over there, but they're instead going to move over over this resistor to C and move over this resistor over to C. Okay, so this condition saying that I read no current over this ammeter is equivalent to saying that B and D are at the same potential. And so if they're at the same potential, you can break the circuit between them, you can connect them to a short circuit. It's not going to change the physics of the circuit. If 2 things are at the same potential, you can connect or disconnect them, it just doesn't matter. Now, if they're at the same potential, however, then the potential difference between A and D and A and B are the same, which means we can write the potential difference from A to D, which is I1 times R1, must be equal to the potential difference from A to B, which is I2 times R3. And we can make the same argument for the potential difference from B to C and D to C. So the current is not going to pass through here. This is still I2. So I2 Rx is going to be equal to, this is still going to be I1 times R2. And we are to solve this in terms of Rx, so let us write this in terms of Rx. Rx is going to be, excuse me, I1 over I2 times R2, but from here we can write that I1 over I2 is equal to R3 over R1. Okay, so I can put this in here, R3 over R1 times R2 is going to be my unknown resistance. So if I can adjust this R3 in such a way that I read no current through this ammeter, then by knowing the values of these 3 resistors, I can deduce the value of the 4th resistor in the circuit. This is how you would use the Wheatstone bridge. For the part B of this problem, they give you some numbers. R1 is 630, blah, 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 but I'm not going to actually carry out the multiplication and division. You can easily do this yourselves. Okay, so that will be all.